Okay, thank you. So in the last class and the class before that, we've been talking about how to find the source of uncertainty in your experimental or model measurements, and also how to quantify that uncertainty in terms of confidence intervals and confidence levels. Okay, and also if you take multiple measurements, what are the important statistical concepts that will give you the uncertainties in the mean uh, or some other statistical measure, and the theorems related to that, the most important of which is the central limit theorem. Now today we will talk more in terms of examples about how to report these uncertainties. And there is a lot of subtlety involved here. And although they're pretty obvious, it's very often that people are not careful about this. So let's see. So suppose I have measured a quantity, let's say a speed v1, and I know that my average speed is 20.2 meter per second. Of course, the unit is always important. Then, and I report an uncertainty after doing some sort of statistical analysis or whatever as 0.3429 meter per second. Now, what is the problem with this? The problem with this is that you have reported the mean to one decimal place and you have reported the error to a larger precision. So this is not possible. So if your actual measurement is to a lower precision, your uncertainty cannot be to a higher precision. So you should report this as 20.2 plus minus 0.3 meter per second. So that is a consistent representation. Let's take another example. Suppose I have another speed, okay, and my mean is 415.1 meter per second. And the error I report after whatever analysis is 10 meter per second. Now this is also weird, because if your error is so large, then this 0.1 has no significance in your reported value. So you should report this rounded off to the nearest 10 over here. So that would be 410 meter per second plus minus 10 meter per second. Okay. So these are common errors that are encountered in reporting uncertainties. Now, how do you denote these things? So this quantity over here, this is what we would call so this uncertainty is called delta V. Now, this delta V also, if you just report a delta V, it does not tell you, so it looks as if this 10 meter per second is a larger uncertainty than the 0.3429. However, the error assumes significance only relative to the actual value. So just the magnitude of the error does not reflect how uncertain your measurement is. So what is better to report is, of course, relative uncertainty. And relative uncertainty, as you can see, is basically delta V by V. So in case of V1, we have 0.3 by 20.2, which is 3 by 202, that's 1 by, okay, some fraction, okay. And in case of V2, it is 10 by 410. Okay. And then you could also report this either as a fraction or as a percentage. So either way, then you would be able to compare how which speed is more uncertain in your measurements. Now, let's say I have a quantity that has been reported with an uncertainty, and I need to do some mathematical uh, operations on these quantities. So then I have to know what to do with the uncertainties and what the derived quantities, or how the derived quantity will, sorry, I mean how much uncertainty will be there in the derived quantity. So I need to be able to calculate that. So let's learn to do that. So if I want to add or subtract, hello, I'm sorry, I think my internet went off. So let's start again. Okay, I hope you all have not missed too much. So if I have two quantities with some uncertainties and I want to add them up, so that in this example I have taken two momenta, then the error in the sum is the square root of the sum of the squares of the quantities being summed. Okay. You can calculate this. I think you will get something. So 0.02 squares, 0.0004 plus 0.0025, and then take a square root. Well, something you can calculate it. And then you can report the P total plus minus delta P total. Okay. Now, if you want to do a subtraction, let's say I have a difference quantity P1 minus P2, then the error in this difference is again delta P1 squared plus delta P2 squared. So it is the same formula as the sum. So this gives you a strange situation. The strange situation is that if the error is the same in both the sum and the difference, then it can well be that P1 minus P2 is smaller than the error, or they are comparable. So if you have a difference, then the uncertainty in the difference is actually, or the percentage uncertainty in the difference is much larger than the percentage uncertainty in the sum. So this is something very important to remember. Okay. So what is important to remember? That if you have a difference of two large quantities and these large quantities have some inherent error, then the error that, or the relative error that you get in your difference can be much larger than what appears to be the error in your individual quantities. So that is why it is never recommended that you compute any small quantity as a difference of two large quantities. Okay. Something I encountered in my own field of research is, for example, excitation energies. So if I compute the state energies of a molecule, let's say the ground state and the excited state, and then I try to find out the excitation energy as a difference of these two state energies, then the relative error in this quantity is much higher than if I formulate my theory in order to get the excitation energy directly. So because the idea is that the error that is introduced in a numerical calculation or in an approximation depends on the quantity being calculated. So if I'm calculating a state energy, these are, let's say, of the order of hundreds of atomic units of energy, and an excitation energy is around 10 to the power minus 3 atomic units of energy. So there's a difference of order of 10 to the power 5. Okay. So this is a very significant difference. So you should never compute something as a difference of two large quantities, especially if you're doing it numerically, where you will have some uncertainty. If nothing else, you will have the uncertainty of numerical precision because of computation. So you can only have up to 16 decimal places in a computer, right? Because of if you have a double real quantity, for example. So because of the inherent error in values present on a computer, or even in errors in your in your theory due to approximations, it's always better that the smallest quantity is approximated, so that you have control over how much error is being introduced there. Anyway, so the next thing, so we've covered addition and subtraction. Now the next is, of course, multiplication and division. So let's go to the next one. So I have two quantities. Let's take momentum again, that is mass into velocity. And my mass is, let's say, 11.2 plus minus 0, 0.2 kg. And my momentum is 5.53 plus minus 0.01 meter per second. Sorry, not momentum, this should be velocity. Okay. So what is the uncertainty in my momentum then? So in multiplication, it's a bit different. So delta. So the formula is that the relative error in the momentum is the square root of the sum of the squares of the relative errors. Okay. And then you will get some value. So in this case, delta P by P is something. Okay. So you'll get some value. Let's say I get K after evaluate the values. From this, I can calculate delta P as K into P. And then I can report P as P plus minus delta P. Okay. This is multiplication. In case of division also, you have the same formula. So let me just put this here then. For division, this same formula. So again, dividing two large quantities to get a small quantity is not a good thing. Much better to cast it as some sort of multiplication or compute the quantity directly. So the takeaway here in case of numerical coding is that as many of the expressions that you code, it should have the least amount of subtractions and divisions as possible. You should remove them by analytic manipulations or algebraic manipulations before you start to code. Okay. Now these are just the simple operations, but what if I have some sort of more complicated expression? So let's say I want to evaluate the kinetic energy, half mv squared, with when there is an uncertainty in my mass and an uncertainty in my velocity. So what would you do then? Then we have to cast things in a more general way. So what is the general way? The general way is that you plot the function in a range of the values. Okay? So here let's first take an example where my mass has no uncertainty. It is some fixed value, m0, and my velocity or speed has some uncertainty. Then I plot the kinetic energy, which is basically a function of V against V, and I get some sort of plot. Now, what does this plot represent? So this plot tells you that if you have an uncertainty of delta V in your speed, then the corresponding delta F in your function is given by the width of this quantity on the y-axis. So once you plot the function, you can find out what error in the function corresponds to what error in the variable. Okay. And how would you express this algebraically? You can say that delta F is equal to df dx, which is the slope over here, into delta x. If x is, okay, in this case I have written it as v, but this is the general expression, so I'll put it as v. So if I know the derivative of my function with respect to the variable, then I can calculate the uncertainty in the function from the uncertainty in the variable. So this is quite obvious in a way. And from this general principle, you can also calculate the formulae that we've been talking about before for addition, subtraction, multiplication, and division. And this can also be generalized to two or more variables. So here I had said that the mass has no uncertainty, but suppose now that my mass has some uncertainty as well, and my velocity is also uncertain, then my delta F is equal to df dm into delta m, or del f del m if I want to be more precise, plus del f del v into delta v. And this can, as you can see, it's perfectly generalizable. So you can you can do this for any number of variables, but look at something here. So it's not directly this, because no, wait, just 1 minute. So the thing is, this is when you have two variables, then it is no longer one straight line, right? So it is then a quadratic function, in which case you will have to take the square of each of these errors and sum them, and then take a square root, because this is a function of two variables. And then from here, then you can generalize to 3 or more variables. I'm sorry for the imprecise statement before. So let's see how the addition and subtraction rules follow from here. So if my function is now x plus y, then delta f is now del f del x, which is 1 into delta x squared, plus again del f del y, so 1 into delta y squared. So that's basically square root of delta x squared plus delta y squared, like we said before. You can, as homework, you can verify this for subtraction, which is obvious, also for multiplication, and also for division. And you will see that in multiplication and division, instead of if you just calculate delta f, then the expression is quite complicated and unsymmetric. And that is why if you go over to the relative error, delta f by f, you will get a more symmetric expression which is easily extendable to larger number of variables. So that is why for the formulae for multiplication and division are reported in terms of the relative errors. The other thing that we have not mentioned before is multiplication by a constant. So if a function of x and y, or rather it's just x, in this case, it's a function of x, is basically the multiplication of a constant into x, and you have some intrinsic uncertainty in x, then what is the uncertainty in cx? That is basically delta f df dx, which is c, into delta x. So all you need to do is multiply the same constant with the uncertainty in your quantity. Okay. And with a combination of all these smaller rules, you can, if you have a very complicated derived quantity and a lot of the variables in them have uncertainties, you have to evaluate the effective uncertainty in your derived quantity by using these rules. So that is the end of the statistical analysis section. Okay. I will now go over to the other section, which is modeling of physical systems, which I said I will also teach. So here, the idea is to formalize or unify all the modeling that we do in various fields. So any sort of scientific study of a system involves modeling, and if you have some generalized concepts, you will see that very diverse ways of handling problems are actually all modeling. So so this part of your syllabus basically wants to give you a perspective on how the various fields are united in their approach and also how they differ in a way. So let's start with a very general overview. So if I want to define modeling, what is modeling? A model is basically a miniature or abstract representation of a real system. So as you see, this is a very, very general definition. So any representation that you do of a real system is a model. And modeling is using these representations, either physical or abstract, to describe a real system. So when you want to explain something about a real system, you will use some sort of representation, whether it's a figure or a formula or a actual model or something. All of these things are models, and anything you do with them is modeling. So if I wanted to enumerate what the purposes of modeling can be, a model can simply be used for concise representation. So for example, if you want to show a potential, show your customer the house that you want to build for them, you might show them a model so that they understand what it will look like. Okay? So it's just a replica, a smaller replica of the original system. It can be for visualization. So something like a map, for example. Let's say the map of India. So no one can actually see India as it is, but if you put a map to it and you explain what the symbols mean and what the colors mean, then people will get an idea of the, let's say, relative orientation of places or physical features in the country, etc. Of course, any sort of visualization is always directed towards a goal. Okay, like we spoke about in data visualization, the first thing you should think about is the message you want to convey through your figure. So if I wanted to show people the states of India, I would show a map like I have here. On the other hand, if I wanted to show people where the mountains were, I would have a map with different features. Okay. Then you might use a model to analyze an experimental result. So this is more a working model. So you might have some results and you want to, let's say, from some sort of molecular analysis or spectroscopy. And then you use a theoretical model to see what sort of molecular structure or what, I don't know, what temperature or whatever replicates that spectra. So that is for analysis of experimental results. You can explore systems unsuitable for experiments. So this is where modeling will stand on its own. So for systems where you cannot do an experiment or you cannot look at the real system, and this can be for various reasons. It can be expensive, it can be risky, it can be simply impossible to do that. A model can be used for prediction. So you might have done some experiment and using the quantities you've found from your experiment, you construct a model and then you use this model to predict the quantities or some other quantities for a system that you haven't done an experiment on. So it can be used for prediction. Or a more obvious model for prediction is our weather prediction software, for example. It uses previous data to predict future data. Then you can use a model for optimization. So you might fit in the parameters of a real system. Let's say you want to optimize vehicular traffic. You collect the data, you fit it to some sort of model, and then you use mathematical analysis to find out what parameters would lead to an optimal traffic system. So the model can help you do the optimization. Then you can use a model for even confirmation of theoretical proposals. So if you have a theory of, say, some forces or some interactions, and you want to verify if that theory is valid, you might want to apply it to some sort of model system. So a simple system where you are sure that your equations can be accurately and reliably solved. You might have a model for that. Some people might even call your theory itself a model, but then that would be a model of uh, the physical forces, for example, while you might have a model of another system or an example system to apply your theoretical model to it and see if it is validated. Okay. So you can use a model for various purposes and in various contexts and also in various fields. So like while I was explaining the purposes, I mentioned a lot of fields. So the number one field today now on everyone's mind is epidemiology. Then you have geography, geology, physics, chemistry, biology, basically any field that deals with data of any kind needs modeling. Okay. So I'm not going into excessive explanations there. One field that I did not speak about is management. So So even management requires modeling. So things like organizational charts. So how to organize people into groups, what tasks to give them. The fact that you make a chart out of it and plot the interdependencies of your employees, that will also be a model of your HR structure. Now, for all these models, the more or less basic classification, or you can group them into three very distinct classes. So this is what I've written as types of models. So this is a physical model, a schematic model, or a mathematical model. Okay. Now this list is by no means exhaustive. So from the point of view of science, I felt that this was the best sort of classification. But if you are from a different field, you might have other types of models as well. So some people, or the criteria in which you classify your models may be different. So I saw, for example, some people classifying models as dynamic and static, but that is not very relevant to us in science. Okay, so the types of models, if you have a physical model, that's basically like having a miniature house or a miniature car or something. Okay. Then you have a schematic model, which is something like a map or an organizational chart or a diagram, for example. And you have a mathematical model. So a mathematical model is basically what is the most relevant to us, and science basically comprises of constructing mathematical models for systems. So a mathematical model constitutes of equations, variables, uh, theorems. Okay, so let's. So your syllabus says just mathematical modeling, by the way. So that's what we will focus on. So mathematical models have different components, among which the equations are the most important. So they tell you the interdependencies of the variables and parameters in your system. You might have a set of formulae for computing derived quantities. You might have a set of theorems governing the domain of your model. Okay. And if you're using a computer for this purpose, then your model would also involve an algorithm. Of course, these equations can be anything of any type. So you know there are many, many kinds of equations. You can have algebraic equations, differential equations, integral equations, matrix equations, all kinds of equations. Now, what are the steps in constructing a mathematical model? So in a mathematical model, you first look at the problem or the situation that you want to model. Then you conceptualize it, or it is called orientation, in the sense you understand the relevant features of the problem and you frame the question. You frame the question or the problem in terms of either mathematics, if you can, or even qualitative. So it may be might want to find the behavior of a variable with respect to another variable, but you have to have a specific question before you can construct a mathematical model. One or more. It does not have to be one question, but they must be specific questions. Then you need to identify the quantities that you can quantify and denote as variables. So that is called mathematization. So you identify what variables you have, what you know, how you want to denote them, okay. Also what you want to calculate. Then you construct your mathematical model from various things. So we will talk about that. So you can construct it from first principles, so basic physics, chemistry, etc. Or you can construct it from some sort of experimental data or some or simply some collected data from online databases, whatever. So you have to figure out how to solve the problem. So that would be your model. So the model is the solution to the problem that you have, to the question that you have framed for your problem. Then from the model, you would use it to predict something or to answer your question. And once you have answered your questions, you have to look at these answers. And if your purpose is simply to analyze, then you have to uh, see if the conclusions that you draw from your model outcomes make sense, which means basically that you have to have some way of validating them. So sometimes the validation is obvious. So you can once you have the model outcomes, you can simply see if it does answer your question or not. It's obvious in a way. Or it might be that there is some ambiguity there. Then you have to either test it on some more sample data and see if your model carries through, or you have to use it to compute some known quantity, something that you know is true, and you see if your model also predicts that. So that is called validation, which is very, very important for a model. Sometimes the validation is simply self-consistency. So you might use your model outcomes and feed it again into your mathematical model and see if your solution remains consistent. So now everything that I am saying, of course, seems vague because you don't have a concrete example in your hand. But the important thing to note is that every step in this so-called modeling cycle is important, and it is something that you do whether or not you identify them as steps in your model. So this is simply formalizing what people already do in every field. Then, so how will you model? So the fact of constructing the mathematical model, so the mathematization part, so that can be done from first principles. I think this is what most theoreticians do, whether in physics or theoretical chemistry or theoretical biology. I don't know, maybe biology it's not so easy to do it, but so this is when you use fundamental laws to construct your model. So first principle models are built on a fundamental understanding of underlying ab initio, which means from the start, physiochemical phenomena such as interparticle forces, fields, matter-energy interactions, heat transfer, mass transfer, etc. So they use fundamental concepts. So the fundamental concepts themselves are also models, but they are models for the more fundamental things, and they are things which already have been validated and accepted. So they are assumed to be the truth when you construct your model, and then you use this and you construct some model. So for example, if you do a classical molecular dynamics simulation, then you would assume the Newton's laws of motion, and that is all. So you would have particles which hit each other and bounce off each other, obeying Newton's laws and conservation of momentum. You could also have some Coulomb laws in effect, like for electrostatic interactions of charged particles. But you don't put in any sort of experimental data or anything else into it. It is simply the physical interactions and the physical principles. Then also so here I'm talking about the most basic sort of fundamental principles, which is interatomic or intermolecular interactions. This is okay, but you can also have a more higher level model from first principles. where you're already using a larger model. Let's say you use a diffusion model and you construct your, I don't know, some sort of model for a factory which uses diffusion for conducting a reaction. So there you use the equations for diffusion. So that would also be modeling from first principles, although the equation for diffusion is not as fundamental as interparticle forces. Okay. So this is what is called modeling for first principles, as long as you do not use empirical data. And this model of from first principles you can validate against experimental observations. So because here you're not using any experimental data, the best validation would be against experimental data if you can find it. The other type of model is a phenomenological model. So a phenomenological model is a scientific model that describes the empirical relationship of phenomena to each other in a way which is consistent with fundamental theory but is not directly derived from theory. In other words, a phenomenological model is not derived from first principles. So what does this definition say? This definition says that if you observe a set of phenomena and you see that they are dependent on each other, and you quantify these dependency and guess or fit a mathematical equation to it, okay, from your observations, this would be a phenomenological model. So here you are not looking at why something depends on something or exactly what is going on. You are simply fitting a mathematical equation to what you are observing. So this is called a phenomenological model. So the video I have linked here is of a phenomenological model of the spread of the coronavirus pandemic. So that might interest you. So this is directly, so here we don't know why what is happening, but we want to be able to predict what will happen. So in that case, phenomenological models turn out to be useful. And it may also be that on observing or constructing this phenomenological model, you might get an idea about the reasons behind what is happening. Okay. So maybe you learn something from the phenomenological model. So you can have two purposes for constructing it. One is prediction, which is the most common purpose. And the second is trying to understand what is happening by quantifying the interdependence of phenomena. Now, this a phenomenological model might incorporate some first principles. So, if you know the reason, the why and how of some part of your phenomena, you might incorporate the first principles there. While the other parts, the parts that you don't know, are simply from observation. And the fact that your phenomenological model will be able to predict something or predict data which is not already incorporated into it is assumed, and there is no guarantee to it. So if you have a model from first principles, you have a fairly good idea of the limitations of your model. But in a phenomenological model, you don't have a fair idea of that. So it might be able to predict. So let's say for the coronavirus pandemic, if you construct a phenomenological model and you predict the death rate 1 week hence, your model may be perfectly good at doing that, or 2 weeks hence, but then it fails 1 month afterwards. Okay. So the predictive capacity is unknown. Now, some surprising models, or some very common models, which were phenomenological models, I've put some examples here. So, Bohr's atomic model, for example, was a phenomenological model. He observed the spectra and suggested that this might be the atomic structure. Similarly, for the liquid drop model of the nucleus. So, here the concepts of fluid theory like viscosity, surface tension, etc., were adapted to describe the nucleus. That is, of course, not true. To describe a nucleus, you need the nuclear forces and a quantum picture. But the liquid drop model worked for quite some time, so that was a phenomenological model. Like I mentioned, statistical models of the spread of COVID-19 and machine learning models. They're also phenomenological models. So they construct relationships between input data or among input data in an ad hoc manner, which fits whatever information is given to it. And it assumes that if it is given an unknown sample, it will be able to do it. Okay? So there is no fundamental principle involved in the algorithm. It's simply phenomenological. Okay. So that is all about the first principles model and phenomenological models. So next class we will talk about dimension and analysis, as you can see, which is a very important concept for constructing mathematical models. So I'll stop here today, and you can stop the recording as well. Does anyone have any questions from today or before?
Hello, ma'am. What you told about the quiz, can you repeat it?
Okay, so we will have a short quiz on Friday during class hours. So Friday we have a class from 4 to 5. So we'll have a quiz in that class. It will be just probably only MCQs, but can be like, 1 line or 2 line questions. Only on the part that I have taught.
Okay, ma'am. It would will be through a Google form or like we
We
learn.
learn. It
Okay,
will be
okay,
through we learn.
okay, okay.
Okay. Uh, I think you all are about more than 100, right? So that I hope we will not have problems with it. We will see. Okay. Please stop the recording. Someone.